Hello and welcome. In this video we want to take a look at Green's theorem again, but this time the different version. This one we're going to call the flux version. Now recall that if you've got a line integral of a vector field along a curve C that we've denoted as f dotted with t ds, can also be written as the integral along C of p dx plus q dy, where p and q are the components of the vector field f. And if C happens to be a simple closed curve, then D is the region inside of it. And Green's theorem says that this line integral is equal to this double integral, where you take the partial of the q here with respect to x and the partial of p with respect to y and subtract them, and then do that double integral. Okay. So now I want to look at the line integral of the vector field across the curve. So this is called the flux sometimes. In previous videos, we denoted this as f dotted with n, the line integral of f dotted with n ds, which what we did is we took n to be perpendicular to t, and we did a particular way of rotating clockwise from where the tangent vector was going. So if the tangent vector is in the direction of x prime comma y prime, then the normal vector was in the direction of y prime comma negative x prime. So where f here is p comma q and n is y prime comma negative x prime, it's the q that gets multiplied by the negative x prime, and it's the p that gets multiplied by the y prime. Hence, things get switched around here, right? That the minus q gets multiplied by the x prime, so that's the dx times dt, right? And likewise, the p gets multiplied by the y prime dt, and that's the dy. If C then is a simple closed curve, we can apply Green's theorem to this. So this is going to turn into a double integral, and this is going to be the flux version of Green's theorem. So Green's theorem says that you got a vector field, you got a line integral that looks like this. You're going to take the partial of this thing right here that's in front of the dy with respect to x, and then you're going to subtract the partial of this thing right here in front of the dx with respect to y. Right? So that's what we did here. This was Green's theorem. This q got partial with respect to x. This p got with respect to y, and you subtracted. So this thing right here gets partial with respect to x. That's this one. And this minus q gets partial with respect to y and subtracted. So the minus negative becomes a plus. So the flux version of Green's theorem says that the line integral around a closed curve C of f dotted with n ds is the double integral over the region inside of C of partial p with respect to x plus the partial q with respect to y dA. Okay. Let's do a few examples here. So my first example here is the vector field f of xy is x plus y, comma, y minus x. Okay. And the curve that I'm going to integrate around is the triangle, which starts at the origin, goes out to the point 1, 0, then over to 0, 1, and then back to the origin. So it's a closed loop, that triangle oriented in that counterclockwise direction. You can see the little pink arrows indicating the direction. Now, as I do this line integral here, this flux integral, I do a couple steps here that I don't necessarily need to do, that I could just use this form of Green's theorem and jump straight from this flux integral to this double integral. Or you could think of it as saying, well, I know what the flux integral is. It's this. And then plugging in p here and q there, multiplied by -1. And now applying Green's theorem to this thing, I would take the partial of this with respect to x and subtract the partial of that with respect to y. But that's the same, exactly the same as taking the partial of p here with respect to x, because that's where p ended up. And then the partial of q with respect to y, this is q, and then you do that with respect to y, and you would subtract it, and this already had a minus sign in, so subtracting the negative anyway, you end up here. partial of p with respect to x is 1. The partial of q with respect to y is 1. And so I've got the double integral over this region of 2. Now, I did set the integral up because I can see that x is running from 0 to 1, and y then runs from, for each x, y runs from 0 up to 1 minus x. So that would be the double integral set up. But when I factor the 2 out of there, I'm just doing the double integral of 1 dA, which is the area of that region, which is a triangle, 1/2 the base times the height. So the area here is 1/2, and then I'm multiplying by the 2, and so I get an answer of 1. Right? Now, what does this flux integral tell us? By getting a positive result, it's essentially saying there's more stuff going out than going in. Right? That this partial p with respect to p sub x plus q sub y is giving us positive numbers when the vector field is crossing the curve with the vector field pointing essentially in the same direction as that outward normal vector. So over here, you certainly have the vector field pointing outward. There's likewise down here, looks like it's pointing outward. On this edge, there's some stuff pointing inward. Okay, but there's apparently more stuff going out than coming in. Right? Now, if you think of this as let's say a velocity field with water flowing along with each of these little vectors as the velocity at that point in time. To say that the flux is positive is to say that somewhere inside that region, there's a source of water because there's more water going out than coming in. So there's a source. And it might be not that there's a particular source, but that every point is essentially a source and a little bit of water is leaking. I think of it as kind of like coming up through the bottom and then spewing out to the side like a spring or something like that. A mountain spring where the water bubbles up and then comes out. And so it's like the ground is porous here and there's water seeping out and going in. There's also, there's also water flowing in. There's certainly water flowing in on this side, and some of that then would flow back out. But there seems to be some being produced inside. There's a source. If this had come out to be negative, I would use the word there's a sink. That is, there's a drain in there that less is coming out than is going in. And so somehow the water is disappearing on the inside. You can think of that as just a negative source, right? So you can think of sources as being either positive sources or negative sources. And to me, a negative source is a sink. It's a place where stuff drains away. Okay. And I note here that if this sum, p sub x plus q sub y is equal to 0, always, if it just happened to have a vector field where the partial of the first component with respect to x is equal to the partial of the second component with respect to y, no, not that they're equal, that they're opposite of each other, so that when you add them up, you get 0, then the line integral, that is that flux integral, will always equal 0. And this is kind of special. This is like the line integrals we had before, right? If we had the line integral along the curve, that f dotted with t ds, if that was always 0, then this was a conservative field, right? And there was a potential function. Now, if this flux integral is always 0 along a closed curve, then we call this a source-free. It's called a source-free field. That is, any closed curve, there's no sources in there. That there's not extra water bubbling out, right, or being swallowed up. So if the circulation is 0 around all closed curves, we say it's a conservative field. If the flux around any closed curve is 0, then we call this a source-free vector field. Okay. And the following theorem says that there's other ways you can think about these source-free vector fields. So here's a theorem. It says if f is defined on an open, simply connected region D, then the following statements are equivalent. That means if you know any one of them, you know all of them. And if you know any one of them is false, then you know that all of them are false. Okay. The flux integral here is equal to 0 around any closed curve. That's equivalent to saying that if you've got two curves, C1 and C2, in this domain D, with the same starting points and the same ending points, so C1 and C2 both start here and they both end there, they may take different paths to get there. But if they're always equal to each other, sorry, if you got a vector field where this is the case, where any two paths that start and end in the same place, then the integral is the same. The flux integral is the same over both of them. Then we call this independent of path. So if the vector field is independent of path, that's equivalent to saying that the flux integral around any closed curve is going to be 0. That's equivalent to saying that there's a stream function, g of xy, such that the partial of g with respect to x is p, and the partial of g with respect to y is p, and the partial of g with respect to x is negative q. That's essentially geometrically saying that the level curves of g are always parallel to the vector field. Right? When you had a potential function, you could find when you had a conservative vector field, you could find a potential function, and that potential function's level curves would be always perpendicular to the vector field, because the vector field would be the gradient, right? And the gradient is perpendicular to the level curves. So now we're going to say we don't want something perpendicular to those curves. We want a function that the gradient is parallel to all those curves. So it's essentially describing the streams. That is, if this is water and you had a point here, where does it go according to this vector field? Okay. And the last thing that all those are equivalent to is to say that partial of p with respect to x plus partial of q with respect to y is equal to 0. Right? In the next section, partial of p with respect to x plus partial of q with respect to y, this is a little foreshadowing, this is going to be called the divergence. Okay. Let's do a couple of examples of some of these ideas. So here's a vector field. F of xy is x plus 2y comma x minus y. And I note that the partial of p with respect to x is just 1, and the partial of q with respect to y is minus 1. They're not equal to each other, but if you add them up, you get 0. So the partial of p with respect to x plus partial of q with respect to y is 0. This is source free. So if I did a line integral around any closed curve, it would equal 0. If I took two paths that started here and ended there, I would get the same result. Right? This is kind of nice from the point of view of thinking about flow. So if you're thinking about water flowing around, and you have 2 points and you connect them with a sort of a loose string, and you say how much water is passing through that string. Well, it doesn't matter if the string is pulled tight or if the string kind of loops around. If it starts here and ends there, it doesn't matter how that string is, the same amount of water is going to have to pass across it. Right? If there was a source somewhere where one arrangement of the string had the source on one side of it, and then you move the string around to the other side, that is, you would enclose that source, then you might have more water going across that string, right? But if you have no sources, then that's not going to happen, and it's the same amount that passes across any curve that starts and ends in the same place. Any two curves that start and end in the same place. So this is source free, and I'm going to actually find what they call the stream function. So the gradient, if this was going to be conservative, I would say the gradient of little f is going to be the vector field. Okay, but I want now something perpendicular to that. So I'm taking the q component and making it the first component for the gradient of g, and I'm taking the p, or the first component of f, and taking the negative of that to make it the second component of the gradient of g. So I'm finding a vector that's perpendicular to my vector field. So the vector field f is given, and I'm creating a new vector field that's always perpendicular to it in that way. Okay. Editor Will here, as I was editing this, I realized that as I'm writing down what the gradient of g should be, I'm doing exactly the negative of what I said it should be up here, right? I said that the partial of g with respect to y should be p. So the second component here should be p, and I'm making it negative p. Likewise, g sub x should be minus q, and I'm just making it q. Okay. So what's happening is I'm getting a stream function that is completely upside down from what I should be getting. Just multiply the answer that I get here by -1, and it'll correspond to what it says here. I'm not really concerned which way it goes. Both of them work as stream functions, just a matter of um, are you flowing with the vector field or are you flowing against the vector field? Okay, so now carry on with the rest of the video. Now, because this is source free, I can take the gradient. Essentially, this is I can find the potential function for this. That is, this now should be a conservative field, right? Is that the case? So the partial of this one with respect to y is -1, and the partial of this one with respect to x is -1. So it's conservative, and I can find the potential function. So I just integrate this with respect to x to get this x squared over 2 minus xy. And if I integrate this one with respect to y, I also get a minus xy, but then plus, no, but then minus a y squared. So the minus xy shows up in both of those. Anyway, this is what's called the stream function. And I've plotted over here on the graph here. I've got the blue arrows are the vector field f, and the red curves are level curves of this function, x squared over 2 minus xy minus y squared. And you can see that those red curves are always parallel to the vector field. Now I want to point out that this vector field is not conservative. That is, if you look at this original one here and you take the partial of this first one with respect to y, you get 2, and if you take the partial of the second one with respect to x, you get 1. Those are not equal to each other. This is not conservative. I don't have a potential function that I can find. Okay, so there's no potential function there. Now, next example. Very similar to this one, right? Because I had x plus 2y and x minus y. Now I just have x plus y and x minus y. And it turns out, right, the vector field looks very, very similar, but it's just different enough that this one is kind of interesting. Because if I look to see if it is source free, I find that it is. Partial of this first one with respect to x is 1. Partial of the second one is -1, just like it was up above. And so you add them up, you get 0. So it is source free. I can find, in a similar way to what I just did, the stream functions, and you see the stream function. And so the level curves are essentially the streams. That is where the water would flow from any point. And I can see that those red curves are all parallel to the vector field. This one, however, is also conservative, because if I look at the partial of p with respect to y, it's 1, and the partial of q with respect to x, it's 1. Those are equal to each other. So this is a conservative vector field, and I can find the potential function. The potential function is x squared over 2 plus xy minus y squared over 2. It's very similar to the stream function, but a little different. And I might be lying to you here. This feels like a typo to me. This is a typo. Let's come back here and change. So yeah, this was a typo. This should have been divided by 2. So the stream function, when I integrate this negative y, it turns into a negative y squared over 2. And that's what that should be. And so now I've got the potential function here. And the level curves for the potential function are drawn in green, and you can see that these are perpendicular to the vector field at any point. So this is a particularly nice vector field. It is a vector field that is both conservative and source-free. And it turns out that when you have a vector field that is conservative and source-free, the potential function, so this f right here, is what's called a harmonic function, a harmonic potential function, and this is the type of function that you need in order to model electromagnetic fields, gravity fields. It needs to be harmonic, and the notion of harmonic is, well, the types of potential functions that can be used are ones that satisfy what's called Laplace's equation. That is, the second partial of f with respect to x and x plus the second partial of f with respect to y and y is equal to 0. And these types of things, these potential functions for conservative vector fields that are source-free certainly satisfy that property, because this thing up here with the pxx plus qyy, well, if capital F is conservative, then the px is the partial of little f with respect to x. Sorry. If capital F is conservative, then p is the partial of little f with respect to x, so px is the second partial with respect to x and x, right? Likewise, q would be the partial of little f with respect to y, and so q sub y is the second partial with respect to y, so y. And when you add px plus qy, you're adding little f sub xx plus little f sub yy, and I'm ending up with 0. And so we have a harmonic potential function. Okay. And that is where I'm going to end this video. Yeah, it's good stuff.